Thank you, sir. So log 0 is minus infinity, log 1 is 0. Okay? So if you draw the log curve, you start from minus infinity and you pass the x-axis at 1 and you keep going up. So log of 1 equal to 0. That's what I mean when it's past the x-axis. So even though the point value is 0, but the area under the curve even though the log value is minus infinity, but the area is not infinity. If you integrate from 0 to 10, you don't get minus infinity, you get that. Minus 10 log 10, 10 multiplied by log 10. Okay? So let's take a look at integration result. Integration result is x log x minus x. If you put 0 in, that is 0. What about 0 multiplied by minus infinity? Equal to what? 0. Really? You don't know actually until, actually you know if, let's say we are not mathematicians, what you say is, hey, polynomial is grow faster than log. You know that, right? Polynomial grow faster than log. So between 1 million and log of 1 million, which one is more? 1 million is small. When you take log, it's small. So polynomial actually grow faster than log value. Right? Exponential grow even faster than polynomial. So when polynomial multiplied by log, hey, log term is slow, but polynomial is fast, so 0 multiplied by log minus infinity, you may say, hey, that is 0. But if you want to do it like mathematician way, you do limit. Limit of that function approach 0 equal to what? If you have 0 multiplied by minus infinity, that's indeterminate form. You have to rearrange it to be 0 divided by 0. And then you use L'Hopital rule, differentiate top and bottom 1, right? And you take the limit again. Do you still record this? Oh, you don't need to do that. You can do Sm dot limit. Okay. Your expression limit of x approach 0. So ans, I take ans to be x multiplied by Sm log x. So you take the limit of this term is 0. Okay? So x log x limit x approach 0 is 0. So Sympy doesn't just do integration differentiation, it can do limit too, and many things more in its documentation. Okay? Alright, let's take a look at this. I have tried. If you just use regular math, ns equal to 0 multiplied math dot log 0. What do you think? Math domain error, class value error, cannot do. Okay? If I use symbolic computation, it tells me, hey, 0 multiplied by log 0, substitute x equal to 0, you get nan, not a number. Okay? You get nan, not a number. But if you do limit, even though the point value doesn't exist, but limit of x approach 0 exists. That's how can you do integration. Okay? Think about this. If you do numerical integration, you cannot substitute the boundary value. You have to be a little bit further away from the boundary. Otherwise, you get minus infinity, and like that's not cool. Okay? All right, now you know how to do integration. Integration log x dx from 0 to 1. That area is minus 1. Okay? And we have integration of x from 0 to y, I get y log y minus 1. So we can do symbolic integration. Now, let's mix them together. So I have a question, integration from 0 to what value of log x dx will make the area equal to 1? How do I do that? Okay. You can integrate it by hand. Once you integrate it by hand, you can use Newton method. Okay, or you can use F-solve. That's not what I try to tell you. Let's make the symbolic calculation with F-solve. Look at this one. I have symbolic integration of log function of x, log x dx from 0 to y. That's the limit of integration. That's my equation, right? Do I want to know the value of this? I want to know when will it equal to 1. So I put answer 2 minus 1 here. Because F-solve solve for the value where fx equal to 0. It's trying to find x where fx equal to 0, right? So my input, I have to move everything to left hand side equal to 0 before I put into F-solve. So I put, you still remember this? Lambdify. Change from Sympy function to be Python function. The parameter or the variable is y, and the equation is this minus that. Okay, so I have minus 1. And this in here. So F-solve requires the initial guess. And my initial guess is 3. Okay. And then I take one of the answer, I get that, 3.5. So if I integrate from 0 to 3.5, 9, 1, 1, 2, 1, 4, 7, 6, 6, 7, I get the area under the curve of log x, natural log x equal to 1. So this is how we mix them together. It's more powerful, right, if you know more. Now you can mix symbolic calculation together with Sympy numerical method. Good? Alright, let's check the answer. So I substitute the left hand side after the integration I have x multiplied by log x. Right hand side I have x, right, is equal to 1, which we expect. So we check the answer is correct. Sympy integrate x from 0 to the answer that we got equal to 0.99999, almost 1, kind of 1, okay? So I check the answer, I told you it's correct. So now you can mix numerical method, Sympy with Sympy, and more, okay? How about we come to this?
That last problem can still solve it with first point iteration.
Huh? What do you say?
The last problem.
The last problem?
Yeah, the log problem.
Log problem?
This one. Yeah, I mean it's something, but the equation.
Okay.
Yeah.
What's about it?
We can still solve it using first point iteration.
I don't know. You try, please. But what I try here, I just F-solve. I use F-solve because it's always converge. It's not always converge, but most of the time it's converge. Fixed point, it takes a lot longer and it may not converge. For this question in particular, I don't know if it converges or not. It may not. Have to try. I really don't know. Okay. And let's move on. Let's combine MP-Math and Sympy. MP-Math is library of Sympy. Okay, so I have to import MP-Math. MP-Math, you have to install Sympy first. I want to calculate EI function When I open Wikipedia and Wolfram website, I have EI function equal to minus integration from minus x to infinity of e to the power minus t divided by t dt. But when I open Sympy library website and documentation when I press shift tab, it tells me minus infinity to x e to the power of t divided by t dt. They're not the same. I did the same. I asked myself, I think it should be the same, but how can it be the same if they are not the same?
They're the same. In fact, if you find the limit, you have to introduce them.
So
Yeah.
I show it to myself, and probably you may show it to yourself later. So you know how to do all this? Okay, not quite. Let's dig down into it a little bit. So I define u equal to minus t. You see that minus t, I want to change minus t to t. Right? So I define u equal to minus t. Okay? So for t equal to infinity, you see that is t equal to infinity. You see that infinity sign? For t equal to infinity, u equal to minus infinity. Good? Mathematically, they don't want you to write it like that. Okay? If you go to math class, they will want you to say limit t approach infinity, you also approach to minus infinity. You cannot write equal sign for infinity, but in this class, please forgive me. Okay, at t equal to infinity, u equal to minus infinity. At t equal to x or at t equal to minus x, which is the bottom one, u equal to x, d of t equal to minus du, right? You put d both sides. Alright, then you substitute in minus infinity to infinity. So I copy this expression. I substitute the value. So at minus x, I put u equal to x. I put that in. Okay. At t equal to infinity, I put u equal to minus infinity. E to the power of minus t, I put e to the power of u. And the bottom one, t, I change to minus u. dt, I change to minus du. Rearrange it, it gives me this. When I change from u to t, they're the same. Now, you're kind of happier. Not very happy, but happier. Okay, let's do import mathmp. Mathmp give me this equation. Okay. mathmp.ei1, ei of 1, it give me, you see this quotation mark? It's kind of string, 1.89511 something. Float of mathmp.ei parenthesis 1, it changed from that string to float. Alright, now let's check. At what x that eix equal to 1? Let's see, we want to know that. So I plot the graph, okay, between x and eix, I get this graph. So it should be somewhere between 0 and 2. I plot the graph first. To plot graph, I use linear space from 0 to 1. When you use 0, 1 like that, it includes 0 and it also includes 1. If you use .arange doesn't include the last number. Okay. Okay, Sympy.optimize.bisect. I put my function in. Okay. This time, my function has to do with mpmat. mpmat.ei. I talk about mpmat and mat separately because mpmat give you more library. If you want something strange like gamma, Bessel, or some strange special function, it may be in mpmat. Okay, so it may be better if you know how to use mpmat. So I have mpmat.ei parenthesis x and convert from mpmat format into float. Okay, minus 1. And my range for bisection is 0.1 and 0.9. X tolerance is equal to that. Then this is my answer. Okay. Check again, mpmat.ei. I get that. So if I don't use bisect, I use f solve, I get the same answer. If I use f solve without, okay, see this time I try to use it a little bit different. I don't have float x. You see that x? I have lambda input as x, float mpmat.di, float x. When I do that, it works. If I don't have float x, I put just x, somehow it doesn't work. mpmat take the input of floating point. Okay, so this is something to keep in mind. Is this going to be in the exam? I don't think so, but if you really want to use this, sometime when you implement it, you get stuck, you can use this as a reference. We are done. Good. Let's do system of linear equation. Okay, system of linear equation. This one, as always, no right reserve, but I create all this. So we talk about solving dense matrix. Dense matrix means you have value almost everywhere. Okay, that's it. That's a dense matrix. So for dense matrix, you can have Gaussian elimination and back substitution. You have LU decomposition or iterative method. For solving sparse matrix, and this one is the tridiagonal. You have Thomas algorithm. Tridiagonal means it's zero everywhere except 3 lines in the middle in the diagonal term from top left to bottom right. Okay, tridiagonal matrix, it appears quite a bit when you do finite difference. Sparse matrix happen quite a lot more when you do 2D finite difference or finite volume, finite element, you get that. Okay, so when you solve partial differential equation, typically your equation become system of linear equation and it's sparse. It's not dense. It's not like number everywhere. Only some location that you have number. Oh, okay. Gaussian elimination. Naturally, did you study this in undergrad? Not in undergrad. Daniel, did you do this in undergrad? You did. Ami? Yes, you did. Joe? You did too. Can you explain me? Help me teaching. You don't want to? You still remember it? No? What about her? Yaba, you still remember this?
Yes.
You studied this 3 times, 4 times already.
Yeah.
You want to explain about it?
So first you wanted to...
Use microphone.
No.
Come
Can
on.
I just stay here?
You didn't pay, right?
Yeah.
Yeah.
How to explain? I just know how to calculate. So first you wanted to eliminate the first value, which is x1. So in this example, you first need to multiply in the first row, for the first equation, you must multiply the 1/2, and you will get the how can I say that? x1 something, and then you
Okay, I don't have enough break.
add them together.
After I sit for a while, I have enough break. Let me continue. Step number 1. It's difficult for her to explain about this because it's not her slide. That's the problem actually. So step number 1, we write equation into matrix form. So to write equation in matrix form, I have to arrange x1, x1, x1 on the same column, x2 on the same column, x3 on the same column, and something else that's not related to x, put it on the right side. Okay, that's how I arrange it. Coefficient, I put the coefficient in my matrix. Okay, 3 by 3. And I put the constant, which is on the right side, in another matrix. 3 row, 1 column. If you multiply it, first row multiplied by this column, 2 multiplied by x1 plus 1 multiplied by x2 plus minus 1 multiplied by x3 equal to 8. So the first matrix multiplied by second matrix equal to that matrix. So it's equivalent to that. Step number 1, everyone can do it, I know that, right? Okay. Now, there are other way to do Gaussian elimination. One of the way, quite popular, you append that into this 3 by 3. So then I have coefficient and constant. Alright? Second step, append it. So now we have matrix of coefficient on the front. John?
Yep.
We have matrix of coefficient on the front. Okay, that's what we have. And we have matrix of constant, that part. So this equation, this matrix is equivalent to these 3 equations. Coefficient, go here. Constant on the right side, go here. You got it, George?
Sorry, what?
You got this? You understand this?
Yeah.
Otherwise, we cannot move on. Alright, elimination process. The basic idea is you try to make bottom left that triangle to be 0. Okay, that's 0, 0, 0. So that triangle you want to be to 0. Okay, and the rest will change. So step number 1, I copy it. Okay, and I do this. L2, L short for line. Line number 2 plus 3 divided by 2 of line number 1 become new line number 2. So let's take a look at line number 2. Line number 2 is this thing, right? That's line number 2. 3 over 2 of line number 1. So divided by 2, that will cancel. Multiplied by 3, I will get 3 on the top. So 3 plus minus 3 will be 0. So basically if I do this, L2 plus 3 over 2 of L1, the new equation will be that one. That's how I eliminate the first element of second equation. Okay, for the first column, I want to eliminate that too, that number 2. How do I eliminate that? I do, hey, let's just add them together. Because I see that, hey, I have 2 and minus 2, right? If I just add them together, new equation, which is line 3, I have that. So now I success. I eliminate that too. First step is done. The top part, I kept it. I don't do anything. Now let's worry about these two. For these two, next step is I try to eliminate that number 2. Okay. So look at this. When I multiply by 3 over 2, I multiply by 3 over 2 for the whole line. So minus 11 has to multiply by what? 8 has to be multiplied by 3 over 2, which is what? 12, and add with line 2, which is minus 11. So 12 minus 11, I get 1 over there. So how do I eliminate this? I eliminate that by line 3. I start with the line that I want to eliminate. I start with line 3. Line 3 plus whatever that number is and whatever this number is. So line 2 multiplied by minus 2. See that minus 2. So that minus 2 is minus of that. Divided by itself, 0.5. Add them together, then I get line 3. So like solving linear equation, you try to eliminate one location by location. Okay? Yes? Okay. You? You get this? Okay. So at the end, we get that. Notice that the first line doesn't change. Okay? Stay the same. So general formula is new line for line ij is line ij minus line ik divided by lkk, okay, multiplied by lkj. So what is that k? You see LKK, every time we divided by LKK, so LKK is the diagonal term. That is the diagonal term. So first time, LKK is number 2, right? When LKK equal to 2, we eliminate anything below that diagonal term. When LKK equal to 0.5, we eliminate anything below LKK. Pivot element is LKK. Pivot element is the element that we use as our basis. So, Temitope, can LKK be 0?
No.
Yeah. If LKK equal to 0, it crash. So this means if you have system of linear equation and somehow that equation, I don't have that term, it doesn't work. This method doesn't work. How do we fix it? We do this.
Show the rules.
We shuffle it, right? So plain Gaussian elimination is done by without pivoting, okay? Done without swapping the row. We will talk about swapping the row later. We swap the row because if the diagonal element is 0, it doesn't work. And you want to maximize the value on the diagonal term. That's make you more accurate answer too. So that's the formula. So you see every time we divide it by new equation is the equation to be used as a base or pivoting equation divided by pivoting element LKK and multiplied by the element of the new equation that is on the same column of that pivoting element, okay? Then you get this equation and then we multiply by the pivoting equation and we do it for every column or every j, okay? So at the end we get, this part everything has to be the old one, not the new one. After we finish it, we get 0 below it. Okay, look at the loop. We have to loop from k equal to 0 to k equal to n minus 2. What is n minus 2? Let's say n is the number of loops. Is it index of row has the leading pivot element LKK, the pivot element LKK, so that is k. So when we do the loop, we do from that is first LKK, that is second LKK, but we never use that number, right? Actually, we don't use that number either. We use that L11, and then we use that L22, but we don't use that L33. Okay, but if we start the index from 0, so if we consider the first line as 0, so we use L00, L11, but not that one. So that line is, you may say, n minus 2. So if n is a number of row, n is 3, n minus 2 is 2. So you do from 0 to 1, right? 3 minus 2 is 1. So do looping for k to make any Lij which is directly below Lkk to be 0. And then we have to do also a loop from I equal to k plus 1 to I equal to n plus 1. I is index for that row, right? We do for so that the number of rows that are below LKK will be like changed. Right? So when we change the pivoting element, the leading element, we change it like that. But when we loop for I, we do every row that is below the leading element. Good. And of course, we do every j. For j, we do for k plus 1 to j equal to n. J equal to n is the augmented part. Early on, we augment that into our matrix, right? So for this matrix, n is 3. So column 0, column 1, column 2, column 3, which is column n. So when we look for j, we have to cover that part too. Alright, so we have 3 nested for loop, and thus we can write a code. Okay? So the process is just that we talk about. So we specify what is the pivoting element. We do everything that below it. For the first column, we move to the next pivoting element. We do everything below it. And if the pivoting element is done, like we reach the bottom right, we stop. We finish Gaussian elimination. Once we do Gaussian elimination, we have to do back substitution. Back substitution allows us to get the actual value. So minus 1 of x3 equal to 1. So x3 equal to minus 1, right? You use that divided by that number. Or x3 equal to a34 divided by a33. What about x2? So you have 1 minus 0.5 multiplied by x3. Then you divide it by 0.5. Or x2 equal to a24. a24 is that term, right? a24 minus a23 multiplied by x3, which is that multiplied by x3 divided by coefficient of that line, or the diagonal term a22. Now you have x2. For x1, you do the same thing. That and that multiplied by that and that, right? You start with 8 minus x2, oh, no. You start with 8, then you minus x2 multiplied by that coefficient, minus x2 multiplied by that coefficient, and divided by a2. All this equation, then you get a1. You like it? You don't really care because at the end you use a SciPy function. So when you do that, you get x1. So we try, before we do anything, we try to write every step out so you know the general step. Then you can summarize it and get the general solution or the general equation. So in general, xn is xnm divided by x or ann. And any I, xi equal to that formula. That's what we just did, right? That's what we just did. But when we do it from last row backward to row 1. Okay? We don't do like in step from 0 to n. We do from n to 0 or something like that. So m is n plus 1, okay, which is that column. And I, we move from n minus 1 which is the last one, to n minus 2 until we get to the first one. The index thing here may or may not match with what we are about to do, but when you see the actual code, you will see what's that about. Okay? But first we have this general equation. So now you understand the concept idea. Partial pivoting. Pivoting this way is, if the diagonal element of the pivoting row is 0, then we have division by 0. We get not a number, not good. If pivoting element is a lot smaller than the one below it, we get error or unstable. So to get the best solution, you want to have highest value on the diagonal term. But that doesn't mean that you can always do that. No, but if possible, at least the diagonal term should not have 0. Because if you have 0, you do this, you divide it by 0, it doesn't work. Okay, more detail will be on Hyperton book. We will go over it. Now let's talk about the theory about LU decomposition. So basic idea of Gaussian elimination is we have elimination step. Then we do back substitution, right? We get every value. LU is to break matrix A to be L and U, lower and upper. Okay, that's LU decomposition. Gaussian elimination need to be done for each pair of A and B. Do you think it's true? Look at this. The step to do this, first thing you append this to the main matrix A, right? You have AX equal to B. You append B to A. And then you do elimination and then you do substitution. So what if the coefficients stay the same, but this constant just changed? What happened to you? Do you need to redo the whole thing? Yeah, kind of. So it's not cool. Okay? You don't like that. You don't want to redo the whole thing. So if you do LU decomposition, if B change, you're still fine. Okay? So LU decomposition or factorization is to change from A to B, L modified by U. And when I mean L, I include the diagonal term. And for U, I also include the diagonal term. Okay? Once we do that, if B change, this doesn't change, right? This stays the same because this doesn't have anything to do with B. So it's good. We don't need to redo the whole thing. But for Gaussian elimination, we have to redo the whole thing. Okay? What do we do next? After we do factorization, we separate A to L and U. Look at this. Instead of AX equal to B, you have A, not A become L and U. So you have LUX equal to B. What is L? L is triangle matrix, right? Triangle matrix. It's just triangle. Do you need to do Gaussian elimination? You can do forward substitution, right? So if you do L and some unknown equal to B, that unknown is if you start with 3 by 3, that unknown will be 3 row, 1 column. So you can do forward substitution to get UX, right? Because the first one is just B1 divided by L11. So you do forward substitution. Then you get, so we say, okay, Ly equal to B. You can solve for Y directly without doing any Gaussian elimination. Right? After you know Y value, you know that Y equal to UX. You have this, right? And U is what? Upper triangle. So you do backward substitution and then you do X. And then you're done. So once you do LU decomposition, then you just have to do forward and then you backward substitution and then you're done. The backward and forward substitution process is not expensive. Gaussian elimination process is expensive because you have 3 nested for loop. Alright? The rest, we will talk it later. For next time, you get exam. Please come on time. Exam time is from regular class time, and you will also have homework as promised. Okay? See you later. Bye bye. If you need me, come see me in class.